Hello friends, this is Coach Veer again on my YouTube channel Coach Veer, and in this video same topic, differential equation, Picard iteration method, but we need to solve simultaneous differential equations where we have same ordinary differential equation, but here we have two dependent variable. Like instead of y we are getting both y and z with respect to x, and x is our independent variable. As you know, ordinary differential equation are those differential equations which has only one independent variable. Dependent can be anyhow, any number, and that's why we differ it from partial differential equations. So let's get on to it and start solving the simultaneous differential equations, and we'll tell you whole working rule for that, and we'll solve examples also. But before that, I request you to subscribe my channel and press the bell icon. Like or dislike, it's up to you. So let's start. So as you already know, differential equations work with these kind of equations where you have f of x, y kind of stuff with initial conditions x naught and y naught. But here I am talking about a differential equation which has not only one, two dependent variable. Let's take it up. So suppose I have a differential equations, let's say dy by dx, and that is equals to some function of x, y, and z. Another differential equation for the same simultaneous equation with respect to z, we are getting a function, let's say z of x, y, and z. So as you can see, the initial conditions we require are y equals to y naught and z equals to z naught at x equals to x naught. This is our initial condition. So how to solve it and what is the method for that? Suppose you want to find the nth approximation for this, then simply you just write yn for the y as y naught plus integral x naught to x function x comma y n minus 1, the previous approximation value of y, comma z n minus 1, and substitute it in here. Same way for the z n, you put z naught plus integral x naught to x function g with x comma y of n minus 1 comma z of n minus 1 dx. If you use these two successive approximation method, you are going to get y and z. So let's proceed with the example so that we understand it in better terms. Let's take up one example. So let's say we have dy by dx given as z and dz by dx given as x cubed by y plus z. These examples have importance. They might get repeated in your exam. So try them with me on this video with your pen and paper, of course. So let's proceed. And initial conditions are very much required in this. So suppose we got the initial condition y equals to 1 and z equals to, let me write y naught so that you better understand it. They are initial conditions 1 by 2 when or where x is 0. So let's write the formula first. So yn is equals to y naught is 1 plus x naught is 0 to x. Now this z is to be written as zn minus 1. So this is yn. Let's write for zn. Zn is z naught is 1 by 2 plus integral 0 to x, this whole function x cubed bracket y of n minus 1 plus z of n minus 1 integral with respect to x. Here I forgot to write here x. So let's proceed. And what are our first approximations? So when we do the first approximation, we are going to write y1 is equals to 1 plus integral 0 to x zn minus 1. So you know it is z and zn minus 1 is 1 minus 1 is 0, so z naught. So I need to put 1 by 2 and differentiate it with respect to x. When I'm going to do that, I'm going to get x by 2 only, because it's quite of simple. Half can be taken out as a constant. Differentiation 1 is to be integrated, that's x. Limit is from 0 to x, so surely x will gonna come out. So let's proceed for the z. Z1 is equals to Z0 is 1 by 2 plus 0 to x cube bracket y. 1 minus 1 is y0. Y0 is 1 plus Z0, because Z1 minus 1 is Z0, so half. So half plus 1 is 3 by 2. So 3 by 2 can be written outside. That's 3 by 2. Let me write 1 by 2 first. So 1 by 2 plus 3 by 2 x cube dx, because half plus 1 is 3 by 2, that is taken out. Now integrate it, you are going to get 1 by 2 plus 3 by 2 x to the power 4 by 4, and when you add it, or let's simplify it, you are going to get 1 by 2 plus 3 by 8 x to the power 4. That's what is our z1. That is the first approximation. Similarly, for the second approximation and the third approximation, like second approximation, you need to write n equals to 2. So we get y of 2 is equals to y0. Y0 is our 1 plus integral 0 to x, and then we need to substitute the x cube, or no, not x cube, z1 value, because 2 minus 1 is 1. You can see it here, y1 z, here the zn minus 1. So zn minus 1 is this whole figure, 1 by 2 plus 3 by 8 x to the power 4 dx, and when you integrate this stuff, you are going to get 1 plus, integrated by your own, and you are going to get 1 plus 1 by 2x plus 3 by 40. I'm just writing it x to the power 5. So same way, if you do it for z2, you are going to get half plus integral 0 to x, that whole 0 to x, y x cube, y of 1 plus z of 1 dx, and then substitute those values. You are going to get z2 is equals to half plus, let's write the solution because that's kind of easy for you to calculate, 3 by 8 x to the power 4 plus 1 by 10 x to the power 5 plus 3 by 64 x to the power 8. Similarly goes for the third approximation, where you can put n equals to 3 and solve the same way, and you will get a y3 and z3, the approximations. Hope you got it. If not, put it in the comment. See you in my next video for this segment. Till then, bye bye.